Okay, so let me go back to this. Okay, so we all know what gases are. As I was saying just now, gases are one of the three states of matter that we're all familiar with. You have solid, liquids, and gases, and we know how they behave in terms of what you can actually see, what you can actually observe. And we can explain what we see and observe based on their behavior, presumably as particles, all right? So if you look at gases at the particle level, at the microscopic level, you would know that gases are composed of particles that are very highly energetic. They are always moving around, bumping into each other, bumping into the walls of the container that they're in. And as a result of that, the property that we can observe as far as gases are concerned is that they flow readily and they occupy the entire volume of their container. Now, from time to time, you'd hear the term vapor in reference to a gas. And this is usually in reference to a substance that would be a liquid at room temperature, but if you elevate the temperature a bit, then it becomes a gas, right? So we talk about, for example, water vapor and methanol vapor, but when it comes to other gases that exist as gases under normal room temperature conditions, we simply call them gases, like oxygen and hydrogen, all right? And what you'll find is that many low molar mass molecular compounds, like water, like methanol, acetone, and carbon dioxide, hydrogen, and so on, they either have a very low molar mass, which means that they will exist as gases, or they can be easily converted to gases from the liquid state. And this here is just a list of various gases and their uses. I won't go into all of them. I can probably highlight a couple. Like, for example, carbon dioxide, which is used in the manufacture of sodas, carbonated beverages. Methane, which is used as a fuel, and we use it also to industrially manufacture hydrogen. And those are just two examples of gases. Now, we're going to get into an introduction into what is called the kinetic molecular theory. And again, this should be a reintroduction, actually, because you should have met this before in your high school or general chemistry courses. So this is the model that is used to basically explain the behavior of gases, and it's based on how the particles of the gases behave, all right? So basically, according to the kinetic molecular theory, the molecules are in rapid random motion. We mentioned that before because they're highly energetic. And the movement of these gases through three-dimensional space is what we call translational motion. And basically what that means is that these particles, they tend to move in straight lines, excepting when they encounter each other or they encounter the walls of the container, right? So that's what we mean by translational motion. Now, the pressure that is exerted by a gas, according to the kinetic molecular theory, is due to the collision of the gas molecules with the wall of the container, right? So basically, if you imagine billions of gas particles in a container, like, for example, this flask, and they're continually moving, and they're continually hitting the walls of the container, we're talking about literally billions upon billions of molecules or particles continually bombarding the walls of the container. Then that is manifested as the pressure that is exerted by the gas on the inner walls of the container, all right? So that's how we use the kinetic molecular theory to explain things like, why is it that gas exerts a pressure? And that's the reason why, because the particles are always moving, they're energetic, and they're colliding with the walls of the container continuously. Another thing we can talk about in relation to the kinetic molecular theory is how the temperature is related to, for example, the pressure, right? Because as we all know from our everyday experience, if you increase the temperature of a gas, everything else being the same, that means that the pressure of the gas would increase. And again, we can explain that based on the kinetic molecular theory, because basically what is happening in this case is that as the temperature increases, you're imparting more energy to the gas particles. The gas particles will move faster, they will hit the walls of the container with more frequency and harder, and therefore the pressure exerted by the gas resulting from all of that will be increasing as well. So as you can see, we can use the kinetic molecular theory to explain these simple observations that are made and other observations that we're going to talk about later on. So we have talked about gas pressure earlier. We're going to define what we mean by this term. Pressure, by definition of anything, is the force per unit area, right? And because we can say pressure is defined as force per unit area. Then the unit of pressure will be some unit of force divided by some unit of area based on this definition, all right? Now, the SI unit of force is the Newton unit, N, and the SI unit of area in this context would be meter squared. So therefore, the pressure units can be expressed in terms of newtons per meter squared. And there's a name given to this combination of units. It's called the Pascal unit, which is abbreviated PA, uppercase P, lowercase a, all right? So that's the unit of pressure according to the SI system. But there are other units of pressure that can be used. Well, there's one which is a derivative of the basic unit here. If you use the corresponding prefixes, so for example, kilo means 1,000, so kilopascals would be equal to 1,000 Pascal. And this is oftentimes used because the Pascal unit is actually a very small unit compared to the kilopascal unit. But there are some other units as well, which are not SI units, but are commonly used in science. There's one that is known as the atmosphere, which we'll talk about shortly. And then there's another one known as the millimeter mercury unit, which is the same thing as a torr unit. And I'm going to explain the origin of the millimeter mercury unit as well, all right? So we can convert from one of these units to another because they're all actually related. And the next slide is showing you the relationships, right? And the Canvas, the tables that I've posted in Canvas gives you pretty much all these relationships. Now, let me just say that I don't anticipate us using all of these, right? For example, at least in this course. For example, I don't anticipate you using the bar unit, the millibar unit, and the pounds per square inch, right? But all the other units you're going to use. Millimeters mercury, torr, newtons per meter squared, which is the same thing as pascals, and kilopascals, all right? Now, so as you can see here, all of these on this side are related to the 1 atmosphere unit, right? 1 atmosphere is equal to 760 millimeters mercury, which is the same thing as 760 torr. And then down here, it is equal to 101,325 newtons per meter squared, which is the same thing as 101,325 pascals, which is equal to 101.325 kilopascals, right? So those are the relationships between all these units on this side and the atmosphere unit, all right? Okay, so let us talk about the instruments that are used to measure the pressure of gases. And the instrument, well, there are two instruments. There's one instrument known as a barometer, which we're going to talk about now, and that is used to actually measure the pressure of the atmosphere, because as you know, the atmosphere is a mixture of gases, the main component being nitrogen, which is almost 80%, and then the other ones would be oxygen, which is just under 20%, and then you have some other gases, right? So basically, we have air. The air that we breathe is actually exerting pressure on everything that is submerged in it, including ourselves, right? So the atmospheric pressure is what we're talking about here, and the instrument that we use to measure that is the barometer. And the definition of the atmosphere unit is the pressure exerted by a column of mercury exactly 760 millimeters high, all right? So this is where we get the relationship between the atmosphere unit and the millimeter mercury unit, right? So 1 millimeter of mercury, I'm sorry, is also called the torr unit, right? So here we have again the relationship between the units, which we mentioned earlier. 1 atmosphere is equal to 760 millimeters mercury, which is equal to 760 torr, which is equal to 101.325 kilopascals, right? So here's where we're going to get into how do we measure the barometric pressure or the atmospheric pressure. And what I'm showing you here on the screen are two setups. The first setup involves a trough filled with mercury. And later on in this class, we're going to learn why mercury is a liquid of choice in this particular type of setup. And we have a tube here, right, where this end is open, right? And if you put that tube, if you insert one end of the tube below the surface of the mercury, what you'll observe is that the level of the mercury outside the tube would be exactly equal to the level of the mercury inside the tube, all right? So therefore, there's no difference in terms of the mercury level outside and inside the tube in this setup. Now, that's what happens over here on the left. On the right, we have a slightly different setup. We still have a trough of mercury. We have a tube, but this time the tube is sealed at one end. I'm sorry about that. So basically, the way this is set up is that you start off with your trough filled with mercury. You fill this tube completely with mercury. You put your thumb over the mouth of the tube, or the open end of the tube, and invert it into the trough filled with mercury, and you let it sit for a while. Now, if the mercury, if the tube is long enough, what you'll find is that the mercury level will fall until it gets to about 760 millimeters of mercury, right? Height inside the tube, right? Now, this column of mercury inside the tube will exert a pressure at this point here, which is level with the mercury level outside of the tube, right? So basically, what we're saying here, the conclusion we can come to here, is that the pressure exerted by this column of mercury at this point here would be equal to the atmospheric pressure that is exerted on the surface outside of the tube. So that's where we get the 1 atmosphere unit. We say that 1 atmosphere is equal to the pressure exerted by a mercury column, which is 760 millimeters tall or high, all right? So that's where we get that relationship from, okay? And of course, as you can imagine, the atmospheric pressure changes due to weather conditions and so on. So therefore, some days you might have the atmospheric pressure being greater than 760, or on some days lower than 760 millimeters mercury, all right? So that's basically how the simple mercury barometer works, all right? And as I said before, mercury is a liquid of choice in this setup, and later on, we're going to see the reason why that is the case. But before we do that, let's look at this example right here. This question says that a Canadian weather report gives the atmospheric pressure as 100.2 kilopascals. So the question is asked, what is the pressure expressed in unit torr, all right? So basically, you're given 100.2 kilopascals, and you're asked to calculate the equivalent unit in torr. So 100.2 kilopascals would be what we're starting off, and we have to multiply by a conversion factor, which allows us to convert from kilopascals to torr. And based on what we saw earlier, we saw that 760 torr would be equal to 101.325 kilopascals, right? So that would be the conversion factor. So all we have to do now is to do our calculation. So we're going to take 760 divided by 101.325, and according to, and then we multiply by 100.2. So according to my calculations, this works out to be equal to 751.2 torr. All right. So that's basically how that is done. All right. Okay. Any questions so far? Any questions? Any questions? Yes, we're using sig figs. In this case here, and who's asking that question, by the way? Okay, first question being asked is, are we using sig figs? And the answer is yes. We can assume that the relationships are exact relationships, as far as this is concerned, right? So basically, we're rounding off the final answer here to 4 sig figs, because we have 4 sig figs here, all right? So that's answering the first question I saw. Let me see here. Now, the second question is, where did we get the 101.325? Because of the relationships that we talked about earlier. Let me go back to that slide. 760 torr is equal to 101.325 kilopascals. So that's where we get that number from, all right? Okay, any more questions? Let me see. Oh, and we're multiplying 100.2 to get the final answer. I don't understand the second part of your question, Miss hold on 1 minute. Yeah, I don't understand the second part of your question, Miss Good. Oh, multiply 760. Hold on. Give me a minute here. Right, you multiply the 100.2 by 760 divided by 101.325. Yes, that's what you need to do. And I think I saw another question just pop up, or maybe I'm mistaken. Okay, I guess I'm mistaken. All right. Okay, let me continue. Before I even continue with the PowerPoint, let me get out of this here and go to, now I've made copies of assignment number 5, but since you guys are not here, then I'm going to see if I can publish it so that you guys can have access to it. And I just want to show you okay, so this is assignment number 5 based on chapter 5, of course. So basically, so far, you should be able to do question number 1, right? So I won't do it right now, but I will allow you to have a look at it, and you can try it on your own. And if you have any problems, feel free to contact me about that. So let me move on now to discussing the other instrument that is used to measure pressure. And this time we use this instrument to measure the pressure of gases. It's called a manometer. And as stated here, the manometer is used to measure the pressure for a sample of gas. And the pressure that is measured directly from this instrument is based on a difference in the heights of mercury or some other liquid, but again, mercury is the liquid of choice, in the 2 arms of the manometer, all right? And the manometer is a U-shaped tube, which looks like this, right? So in this particular setup, you have your U-shaped tube with your gas in it. Presumably, there's no gas inside here, in this part right here, where it's sealed. And you have this part here connected to your container with the gas. So you open this up, the gas flows, it exerts a pressure on this end, it pushes up the mercury level in the other end, and the height difference between the mercury level here and the mercury level here would be proportional to the pressure of the gas. So basically, if we measure this height difference in terms of millimeters mercury, then we can simply record that as the pressure exerted by the gas in millimeters mercury, basically, all right? So as stated here, if the liquid is mercury, you can definitely express delta H in terms of those units, right? Now, if you're using some other liquid, then you can calculate the pressure in pascals using this equation right here, right? Pressure is equal to G times D times H. Now, G is a constant, which if you have done physics before, you should have met it, right? It's called the acceleration due to gravity, all right? It is basically the acceleration of any falling object on Earth, all right? D is the density expressed in kilograms per meters cube, and H is the depth below the surface in meters, all right? So H would be the same thing as delta H here, because we're talking about the pressure exerted by the column of mercury at this point here, which is directly level with this point right here, all right? So basically, this is what you'd use to calculate P if you want to express the P in pascals, all right? And again, mercury is the liquid of choice, and you're going to see how the use of this equation shows that mercury is the best liquid of choice to use in these instruments. But before we do that, we have to look at some other types of manometers, because you'll notice at the top here it says a closed end manometer. In other words, this end is closed. But you have another type of manometer, which is open-ended, right? And here we have two situations involving an open-end manometer. So it's basically the same setup as before. The only difference is that this end is now open to the atmosphere, all right? So basically what will happen is that you'll have two types of pressures acting on the separate surfaces in the tube, right? You have the atmospheric pressure, which is acting on the mercury level or surface here. And then you have the pressure of the gas, which is acting on the surface of the mercury in the other part of the U-tube, right? And basically, the height difference between those two mercury levels will give some means of calculating the pressure exerted by the gas, right? Which is the aim of the manometer. The manometer is used to measure the pressure of the gas. So basically, what will happen is, in this case, on the left, you have the mercury level here, which is at a higher level compared to the mercury level here. So what that tells me is that the pressure of the gas exerted here would be greater than the atmospheric pressure. And by the way, you'll notice that this is called P bar. Bar is basically short for barometric. So barometric pressure, atmospheric pressure, both the same thing, all right? So basically, we can conclude that the pressure exerted by the gas is greater than the pressure that is exerted by the atmosphere, P bar, and the difference between those two pressures will be equal to delta H, right? So therefore, we can write down a relationship between P gas and P bar, and that is this right here. The pressure of the gas would be equal to the barometric pressure plus delta H, and that's what we have here, right? So if you want to find the pressure of the gas, you need first know what the barometric pressure is. You measure the height difference between the two mercury levels, and then you add these two together, and that gives you the pressure of the gas, right? So that's what happens in this case, where the pressure of the gas is greater than the pressure exerted by the atmosphere. In this case on the right, it's basically the opposite in terms of the mercury levels. The pressure of the gas here, of course, would have to be less than the pressure exerted by the atmosphere here. The difference between those two pressures would be equal to delta H. So therefore, we can write down a mathematical relationship between the two, where the barometric pressure will now be equal to the pressure of the gas plus delta H, and that's how we end up with this equation right here, all right? And therefore, if you want to find the pressure of the gas, you definitely have to find the difference between the barometric pressure and delta H, right? So that's basically how we use the manometer, the open-end manometer, to calculate the pressure of the gas that's in the container. Now, here we have a question in this green box right here. Oops, right here. It says for part B, what is the pressure of the gas if delta H is 100 millimeters of mercury and the barometric pressure is 760? So basically, all we have to do is rearrange this to get, let me squeeze it in. Let me do it right here. The pressure of the gas would be equal to the barometric pressure, minus delta H, which would be equal to 760 millimeters mercury minus 100 millimeters mercury, and that will be equal to 660 millimeters mercury. And that's how you do that, all right? So that's basically how we use the open-end manometer to determine the pressure of a gas. And in order for us to do that, we need extra information. We need the barometric pressure, the current atmospheric pressure, all right? Okay, any questions about this? Any questions about this particular example? Okay, all right. So let me go back to the assignment, because I think the next question in the assignment deals directly with this sort of situation. Okay, so here we have a situation, or three situations. it says if the atmospheric pressure is 0.975 atmospheres, what is the pressure of the gas in the enclosed, the pressure of the enclosed gas in the left arm of the tube in each of the cases below, right? So you're given three situations here. This first situation here is where in the left arm, right, you have the gas trap here, and the other side here is sealed, right? So this is a closed manometer that we're dealing with right here. So let's deal with that one first. So let me get my writing thing out. Okay, so in this case here, we have the gas that is trapped here. In fact, we have the gas trapped in the left arm in all cases, all right? So you have the gas trapped here, right? And presumably this is a vacuum because this is closed, right? So the question is, what is the pressure of the gas in the enclosed region right here? And the answer in this case is that since there's no gas here, this is a vacuum, right? Since there's no gas here, that means that the pressure of the gas would simply be equal to H, which is 45 millimeters. So therefore, the pressure of the gas in this case would be equal to 45 millimeters mercury. All right, so that's a relatively simple situation. Now, this one is not as simple because now we have the barometric pressure, P bar, acting on the surface here because this is now open, right? So the difference in the height levels between between the mercury level here and here is H, which is 78 millimeters, right? So because the pressure exerted here would be greater than the pressure exerted by the atmospheric pressure, we can write down that P gas is equal to H plus P bar. All right? Now, they gave us P bar as 0.975 atmospheres, and H is given in millimeters mercury. So basically what you'd have to do is either convert the atmospheres to millimeters mercury or vice versa. So basically what I'm going to do is convert 0.975 atmospheres to millimeters mercury. So you're going to have 1 atmosphere here, 760 millimeters mercury above, and we do that calculation. So that's 0.975 times 760. And according to my calculations, this works out to be 741 millimeters mercury. And now that we have the barometric pressure expressed in millimeters mercury, we can now do this. We can add the 78 millimeters mercury to the 741 millimeters mercury. And that would give us the pressure of the gas, which is 819 millimeters mercury. And that's how that is done. All right? Any questions about this? Any questions? Okay. So let me have you take a stab at this one right here. All right? Now, in this case, it's the flip side in terms of the mercury levels compared to the second one. In this case here, the mercury level here on the enclosed side is at a higher level compared to the mercury level here, right? So how would you set up the equation relating the pressure of the gas here and the barometric pressure here? What's the relationship between the two? Well, any ideas? What I'm asking for is something looking like this. Not quite the same, but something looking like that. Okay, let's see here. We would set it up like the last question and give me, oh, okay. Well, let me give you a hint. You have to look at which one is greater. Which one has a greater value? Is it P bar or is it P of the gas? Okay, let's see what you have here. Okay, so P bar, you're saying that P bar is equal to P of the gas minus H. So that's what Miss that's what Miss Maya is saying. So Miss Good, do you agree with that?
Yes. I'm just a little confused
Mhm.
about how we're plugging in the atmospheric pressure. Can you is the atmospheric pressure, are we plugging that in for P bar or PG at all or no?
Right, for P bar, the atmospheric pressure
Okay.
is right. P bar, the bar in the P bar stands for barometric, right? So
Mhm.
the barometric pressure is the same thing as the atmospheric pressure.
Okay, I was just making sure.
Yeah. But I want to, so do you agree with this?
Yes.
Okay. I don't agree with it, right? And the reason why is because, as I said before, you have to look at which one is greater based on the experimental setup right here, right? Obviously, if you think about it, if the mercury level is pushed down here and is higher here, that means that the barometric pressure would be greater than the pressure of the gas, right? So that means that the barometric pressure would be equal to the pressure of the gas plus the H, which is the difference in the mercury level. All right? Everybody get that?
So it's just going to be the same equation as it was before,
No,
except
it's not
we're
the same. Compare
okay.
these two. It's not exactly the same. In this case, the pressure of the gas is equal to H plus P bar. In this case, P bar is equal to the pressure of the gas plus H. So those are two different equations. Okay, somebody, let me see here. Oh, so Miss Mayer just, okay, she's agreeing with me now, all right? But Miss Good, do you see what I'm talking about? Miss Good? Oh, okay, good, all right. Um, so basically, now remember, the question is asking for the pressure of the gas, right? So the pressure of the gas would be equal to P bar minus H. And then P bar is, as we calculated before, is 741 millimeters mercury. And H is 67 millimeters mercury. So let's see what that gives. 741 minus 67. So according to my calculations, this works out to be equal to 674 millimeters mercury. All right. And that's basically how that is done. Okay. All right. Any questions about this? Any questions? Any questions? Okay. All right. So let me clear this. I hope it's okay for me to clear this. Let me clear this and then get back to the PowerPoint. Where is it? Where is it? Where is it? Okay, so all right, now this here is a question which illustrates the reason why. Um, sorry. The reason why mercury is the liquid of choice when it comes to instruments like the barometer and the manometer, all right? So this question says, calculate the height of a column of water, and it gives the density of water, which is 1.00 grams per cm cube, that exerts the same pressure as a column of mercury, and it gives a density 13.6 grams per cm cube, 760 millimeters high, right? Now, the equation, I've already worked it out here. I think I was recording a video when I did this, so I'm just going to show you using what I have here already. So here we have the equation which I introduced to you earlier. The pressure exerted by a column of liquid is equal to the height of that column times g, the acceleration due to gravity, times d, which is the density, right? So that's the equation for calculating the pressure exerted by a liquid column. Now, the question says that the column, in this question, the column of water exerting the same pressure as a column of mercury. So the first thing I'm going to do is set the pressure exerted by the water is equal to the pressure exerted by the mercury. And then what I'm going to do is write this part here for each of these terms, right? So basically this expression here, in part for the water, and the same expression for the mercury. When I do that, this is what I end up with. The height of the water column times g times the density of the water is equal to the height of the mercury column times g times the density of mercury. And then what I would do is to find the height of the water column, which is what the question is asking for, I would divide both sides by the density of water. So that's why this cancels with that. And the g's will cancel out as well, right? So I'm going to end up with this equation. I don't know if you can see it clearly down here. In fact, maybe it's not as clear. So let me see if I can write it up here. It is the height of the water column is equal to the height of the mercury column times the density of the mercury column divided by the density of the water, right? And then when I put those numbers here in this expression right here and do the number crunching, I end up with this answer, which would be 10,300 millimeters, right? So basically that's the height of the water column that you'd need to exert the same pressure as 760 millimeters of mercury. Now, 10,300 millimeters is the same thing as 10.3 meters, right? And to give you an idea as to what 10.3 meters look like, my height, and I'm quite sure you know how tall I am by now, my height is just under 2 meters, right? That's my height. So if you were to use water instead of mercury in an instrument such as a barometer, you would need to have a column which would be 10.3 meters, which would be 5 times my height. And as you can imagine, that would be a very inconvenient setup for measuring the atmospheric pressure, right? So this illustrates the reason why water, which is cheap, certainly much cheaper than mercury, right? Water is not used for this purpose because you need a very long tube in order to basically support a water column. And that's the reason why mercury is used, because mercury does not need as high a column as, or higher tube, or as long a tube as water, right? And the main reason is that it comes down to the density, the relative high density of mercury compared to water, right? Water, its density is 1 gram per mil. The density of mercury is 13.6 grams per mil. So basically, mercury is the best liquid for this type of instrument. Okay, so much for that. So now we're going to get into the different laws that govern the behavior of gases. And as I said before, you should have met these topics, and especially these laws from your previous experience. So I'm going to go through them rather quickly. And the first law we're going to talk about is a law which relates the pressure of a gas to its volume. That is known as Boyle's law. And basically what this law says is that for a fixed amount of gas at a constant temperature, the volume of the gas varies inversely with its pressure. That's one way of stating it. Another way of stating it is that for a fixed amount of gas at a constant temperature, the product of the pressure and the volume is constant. And mathematically speaking, we can express it this way. PV is equal to a constant, or P initial times V initial is equal to P final times V final. Or I like to do it this way, P1 V1 is equal to P2 V2, right? So basically, that's what Boyle's law is all about. Now, this way of expressing it is very useful, especially when it comes to problem solving, because if you know 3 of these terms, you can determine the 4th one. So for example, if you're asked to find the second volume or the final volume, you take the initial volume times the initial pressure divided by the final pressure, and that gives me the final volume. So it all depends on what you're trying to achieve in terms of problem solving. So we can also represent Boyle's law using the appropriate graphs. The graph that you see here on the left is basically showing you the relationship between pressure plotted on the y-axis versus the volume, which is plotted on the x-axis. And you see how the curve is formed. And basically what that shows you, for example, that if you were to reduce the volume from 4V to 2V, then correspondingly the pressure would increase from 1.0 atmospheres to 2.0 atmospheres. And then if you reduce that further by another half, then the pressure would increase by another double, all right? So that shows you the relationship between pressure and volume directly. Now, the plot here on the left, on the right, is a plot of 1 over P versus the volume. Now, if you think about the equation that I gave you before, or one of the equations expressing Boyle's law, that's PV is equal to a constant. I'm going to call the constant K, right? Now, I can rearrange this to get 1 over P is equal to 1 over K times V, and this would be equal to K prime V, which is another constant. So if you plot Y versus, this should be V here. If you plot 1 over P on the y-axis and V on the x-axis, you're going to get a straight line where the slope would be equal to the constant that you see there. And that is what is being demonstrated here. When you plot 1 over P versus the volume, you're going to get a linear plot, all right? So that's basically showing you the relationship between pressure and volume as described by Boyle's law. Okay, so let's look at this example. It says a helium party balloon has a volume of 4.5 liters at sea level, and the atmospheric pressure is 748 torr. Assuming that the temperature remains constant, what would be the volume of the balloon when it is taken to a mountain resort at an altitude of 2,500 meters, where the atmospheric pressure is 557 torr? And as with all of these types of word problems, you need to be able to pick out the essential information that is provided. So the first thing I'll notice is that you're given an initial volume here, that will be V1. You're given an initial pressure here, that will be P1. And the final pressure here is P2. And the question is asking for the V2, right? When the pressure is P2. So basically we can write a form of Boyle's law. It says V2 is equal to P1 V1 over P2. And then you put the numbers in. P1 is equal to 748 torr times V1, which is equal to 4.50 liters, all divided by P2, which is 557 torr. And then you do your number crunching, 748 times 450. 748 times 4.50 divided by 557, and you're going to get your answer being equal to 6.04, and the units would be liters because the torr units will cancel out here and here. So that's basically how you would do that particular problem. All right. Any questions about this one? Any questions about this example?
So the altitude, the 2,500 meters, like we don't need that at all.
Nope.
Okay.
Don't need that at all, not for this problem. One thing I want to say about the use of the Boyle's law equation is that it doesn't matter what the units of pressure and volume are, all right? But they must be the same on both sides. In other words, the units for P1 must be the same as the units for P2, and the units for V1 must be the same as the units for V2, right? But it doesn't matter what those units are. So for example, P1 and P2 could be atmospheres, it could be torrs, it could be pounds per square inch, it could be literally any pressure units, right? But they must be the same. And the same is true for volumes, for V1 and V2. The units could be gallons, liters, milliliters, it doesn't matter as long as the units are the same. And I mentioned that because sometimes you might get a problem where, for example, P1 is in torr and P2 is in atmospheres. In that kind of situation, you have to do some conversion first before you plug the numbers in. So you either have to convert the units in torr to atmospheres or the units in atmospheres to torrs, and then you plug the numbers into the Boyle's law equation to solve whatever you're asked to solve, all right? So I thought I should mention that. Okay, so let me scroll down to the next slide. And here we're going to deal with another law, Charles' law. Charles' law describes the relationship between temperature and volume for a gas. And basically what this law says is that the volume of a gas, or I should say a volume of a fixed amount of gas at constant pressure is directly proportional to its Kelvin temperature. And this is very important. The temperature must be expressed in Kelvin, all right? In order for this law to work, all right? So it doesn't matter what the volume units are, but the temperature units must be in Kelvin. This brings us to the concept of what is called absolute zero, right? And this is the temperature obtained by extrapolation of this law to zero volume. And this represents the temperature at which the gas molecules have absolutely no kinetic energy. And let me just say that this is a purely theoretical concept. As far as I know, this has not been proven to be true, but this is predicted based on the trend of plotting volume versus temperature, and you see where it extrapolates to, which I'm going to show you shortly. But before we do that, let me just say that absolute zero on the Kelvin scale, when expressed in Celsius, is equal to minus 273.15 degrees, all right? And that means that at 0 Kelvin, the temperature expressed in Celsius is that, right? So that's what we call absolute zero, right? And this is the plot I was referring to. So what was done here, just to explain, is that they're plotting the volume of a gas versus the temperature. So what they did was that they start from a high temperature, and then they record the volume, and then they lower the temperature, and they correspondingly record the volume when it's lowered. And they just continue doing that until the gas becomes a liquid. So now that it's a liquid, we cannot do any more measurements of volume versus temperature as the temperature is lowered. So what they have done is that they extend this line beyond the boiling point of the liquid and see where it cuts the x-axis. And it was found that it cuts the x-axis at, as I said before, minus 273.15 degrees Celsius, right? So what this seems to indicate is that if the gas were to exist as a gas at extremely low temperatures, then basically the gas would have no volume whatsoever at this temperature, because that's basically what the plot suggests, right? So basically that's where the whole concept of absolute zeros came from. Basically, it is saying that at absolute zero, the gas molecules will have absolutely no kinetic energy whatsoever, right? So as a result of that, the Kelvin scale was developed where basically this point here, which is minus 273.15 degrees Celsius, that is called 0 Kelvin. And therefore, the Kelvin scale is basically based on that, all right? So that's why it says here, extrapolation to the lowest possible volume gives the lowest possible temperature, which is the 0 Kelvin that we made mention of, all right? So that's basically where we get the Kelvin scale from in relation to the Celsius scale when it comes to measuring temperature. All right, so based on what we have just looked at, Charles' law, we can do this question. This question says, a balloon indoors where the temperature is 27 degrees Celsius has a volume of 2.00 liters. What will be its volume outdoors when the temperature is minus 23 degrees Celsius? And it says here, assume no change in the gas pressure, all right? So, oh, there's one thing I should have mentioned before we even, how could I forget? I should have mentioned here, right? Charles' law can be expressed mathematically as V1 over T1 equals to V2 over T2, right? Another way of stating it is V1, or I should say V divided by temperature is constant, all right? So this equation is what we're going to use in the example that we're about to look at, because you can use this equation to solve for one of these if you know what the other three terms are. Remember, the temperature that you're going to use here and here must be expressed in Kelvin, all right? Okay, so with that said, let me go to the question now. So basically, as I said before, we'll be using Charles' law, which is V1 over T1 is equal to V2 over T2. So again, we have to identify the different terms. In the question, they gave you the initial temperature, so that's T1. They give you the initial volume, that's V1. And here they give you the final temperature, which is T2, all right? The key thing you need to remember, of course, is that the temperatures must be expressed in Kelvin. So all you have to do is add 273 to the temperature in Celsius, which I'm about to do right now. So in the case of 27 degrees, that would be 300 Kelvin. And in the case of minus 23, that would be equal to 250. So T2 would be equal to 250 Kelvin, all right? So basically the question is asking for V2. So V2, based on this equation, would be equal to V1 over T1 times T2. And then we put the numbers in. V1 is 2.00 liters times T2, which is 250 Kelvin, divided by T1, which is 300 Kelvin. And then we do the number crunching, 2 times 250 divided by 300. So according to my calculation, this works out to be 1.67, and the units would be liters. And that's how you do that. All right? Okay, any questions about this one? Any questions?
So we converted the 27 and the negative 23 Celsius to Kelvins whenever we did that.
You have to, right? Whenever you're using this law, and in fact, for future reference, whenever you're doing using any of the laws that we're going to cover in this chapter, you need to convert any Celsius values to temperature before you can plug those numbers into any of those equations, including this equation right here. All right? I see a question. Oh, okay. I thought I saw a question. All right, so that's basically how this is done. Again, it doesn't matter what the volume units are, as long as they're the same on both sides, right? The volume units for V1 and V2 must be the same, but the temperature units specifically must be expressed in Kelvin, all right? Okay, any other questions about this? Any other questions? Any other questions? Okay, so next slide, we'll be dealing with another relationship, and this is called Avogadro's law, and this law covers the relationship between the moles of a gas and the volume, all right? So this law says that at a fixed temperature and pressure, the volume of a gas is directly proportional to the number of moles or the number of molecules of a gas, all right? So we can express it this way: the volume is directly proportional to the number of moles, or we can express it this way: the volume is equal to a constant times the number of moles, and this is basically saying the same thing. Another way of stating it is, we do it up here, V1 over N1 is equal to V2 over N2, all right? So again, this is useful because you can use this to determine one term if you know what the other three terms are. Now, at this juncture, I want to reintroduce, because you should have met this before, the concept of STP. STP is the abbreviation for standard temperature and pressure, right? And this is necessary sometimes, because sometimes we have to make meaningful comparisons between different gases. And because the properties of gases vary widely, especially when it comes to temperature and pressure measurements, what we oftentimes have to do is choose a standard for temperature and pressure so that we can hold those standards and therefore make comparisons between gases based on those standards. So the powers that be decided to agree on a set of standards where the standard temperature is 0 degrees Celsius, which of course is the same thing as 273 Kelvin, and 1 atmosphere, which of course is the same thing as 760 millimeters mercury, all right? For most intents and purposes, we're going to use 1.00 atmospheres as far as the standard pressure is concerned, all right? Okay, so that's basically what we mean by STP. So whenever you see a question which talks about STP conditions, you should immediately remember that we're talking about conditions where the temperature is 0 degrees Celsius and the pressure of any gases involved would be 1 atmosphere. Another term that you should have met before in your introductory or high school chemistry is this term here, molar volume of a gas. And by definition, the molar volume of a gas is the volume occupied by 1 mole of the gas, all right? That's a molar volume. So basically, that's a molar volume, and it turns out that for all gases, the molar volume is the same under the same conditions. And specifically when it comes to STP conditions, the molar volume of any gas, and you see the term ideal gas here, we're going to talk about that term later on, but for now, we're just going to assume all the gases that we're dealing with are ideal. So under STP conditions, the molar volume of any gas will occupy a volume of 22.4 liters, right? So this is the molar volume of any gas under STP conditions, and this will become important in some future calculations that we are going to come across, all right? Okay, so that's Avogadro's law. Now, unfortunately, I don't have any questions in this slide. But let me check the assignment here. If there's a question dealing with okay, I don't see any questions here, but hold on. Okay, so this is a Charles law. That's a Charles law question. This is a Boyle's law question. Okay, I don't see any Avogadro's law question here. But basically, it's kind of similar to what we saw in the case of Charles law, where you could be asked, you could be given V1, V2, and N1, and you're asked to determine what N2 is, and you do the same algebraic rearrangement to solve for N2, and so on. Okay, so somebody's asking, do we need to memorize these formulas? Okay, the simple answer is that in Canvas, you're given the combined gas law, which we're going to look at later on, which is a combination of all the laws that we have been looking at so far. So that equation will be given. Based on the combined gas law, you should be able to derive all these other laws that we just looked at. Okay, somebody's asking, is question number 5 not Avogadro's law? Let me see question number 5. No, it's not Avogadro's law. It's actually the ideal gas law, which we'll talk about shortly. All right. Okay, so let me go back to the PowerPoints. Okay, the next law we're going to talk about is Gay-Lussac's law, which describes the relationship between the pressure and the temperature of a gas. And this is something, again, we should be familiar with. At a fixed volume and moles of gas, the pressure of a gas is directly proportional to the temperature expressed in Kelvin. So these are different ways of expressing it. Another way of expressing Gay-Lussac's law is, you know what, let me use, hold on a minute. Okay. Let me do this. Okay, so another way of stating Gay-Lussac's law is P1 over T1 is equal to P2 over T2, all right? So that's Gay-Lussac's law, very similar to the Charles law. The only difference is that here in Charles law, you'd have V1 and V2. In this case, you have P1 and P2. Again, the temperature must be expressed in Kelvin, right? The pressure units can be pretty much any units as long as P1 and P2 have the same units, all right? But the temperature units must be Kelvin, all right? So that's Gay-Lussac's law. And let's see if we can solve this problem here based on what we have learned so far. It says, calculate the volume occupied by 4.11 kilograms of methane at STP. Okay, so remember now the question says STP, which stands for standard pressure and temperature, all right? So basically you're given 4.11 kilograms of methane, and you're asked to determine the volume, presumably in liters, of methane under STP conditions. All right? So the first thing I would do is I would start off with the 4.11 kilograms of methane, and I would convert that to moles, but first I have to convert that to grams. So that means that 1 kilogram here of methane will go down here, and here we're going to have 1,000 kilograms. I'm sorry, 1,000 grams of methane above. And then the next conversion factor is where I convert to moles. I'm going to have 1 mole of methane here. And the molar mass of methane would be 12.01 plus 4 times 1.008. So that's equal to 16.04 grams of methane. And then now, because we know we're talking about STP conditions here, in the next conversion factor, I can write down 1 mole of methane will occupy a volume of 22.4 liters, because that is the molar volume of every gas, or I should say every ideal gas under STP conditions. So this will go with that will go with that, this will go with that, and then you do the number crunching. 4.11 times 1,000 divided by 16.04 times 22.4. And according to my calculations, when rounded off to 3 sig figs, this becomes 5,740 liters of methane. And that's how that is done. All right. Any questions about this one? Any questions? Any questions? Any questions? Going once? Okay. Let me see what's next. Okay, so we have learned these 3 laws: Boyle's law, Charles' law, Gay-Lussac's law. And you'll notice while I was discussing, or maybe I didn't say it, but it should become evident, that in order for these laws to work, I'd have to hold something constant. So for example, in the case of the Boyle's law, in order for Boyle's law to work, the pressure, I'm sorry, not the pressure, okay, what is this thing? Okay, so in order for this law to work, the temperature and the number of moles must be constant in the case of Boyle's law. For Charles' law, in order for this equation to work, the pressure and the number of moles must be constant. And finally, in the case of the Gay-Lussac's law, the pressure and temperature must be constant, right? So this begs the question, what if pressure, temperature, and volume changes simultaneously? Then we can basically end up with the combined gas law. Now, in most textbooks, the combined gas law would not include the N here because we would assume that N is constant, right? So in most textbooks, you're going to see P1 V1 over T1 is equal to P2 V2 over T2, all right? So that's a combined gas law, all right? And this is basically the law that you use when you're changing from one state where you have P1, V1, and T1, and then you move to another state where the pressure, volume, and temperatures will be P2, V2, and T2. And therefore, you can solve for any one of these terms if you know the other 5 terms, right? Of course, you have to do some algebraic rearrangement in order to achieve that, all right? Okay, so this is going to be the last thing thing we're going to talk about. Let me see if I can get this done within the last 5 minutes. It says a flask pictured in figure 5.11 contains oxygen. The one on the left is under STP conditions. The one on the right is at 100 degrees Celsius. What is the pressure at 100 degrees Celsius? So the equation that comes to my mind is this equation right here that we just saw. And the first thing I'm going to say here is that because the flask is the same, the volume would be the same. So therefore, we can cancel out V1 and V2 because they're the same. So this is reduced to P1 over T1 is equal to P2 over T2. Then I'm trying to find P2. So P2 will be equal to P1 T2 over T1. And then I'd plug in the numbers. However, we have to make sure that we have the right units in terms of the temperature. So for T2, that's 100 degrees Celsius, which would be equal to 373 Kelvin. So that's T2. And STP, T1, would be equal to 273 Kelvin, which is 0 degrees Celsius, right? So we put the numbers in, where P1 is equal to 1 atmosphere, that's standard pressure, times T2, which is 373 Kelvin, divided by T1, which is 100 Kelvin. I'm sorry, 273 Kelvin, my bad. And we work that out. So it's going to be basically 373. See, 373 divided by 273. So according to my calculation, this works out to be equal to 1.37 atmospheres. And that's it. All right. Okay, so we have to stop here, but let me just say that based on what we have covered so far, you should be able to do all questions up to question number 6. All right. So try those questions. Again, if you have any issues, please feel free to contact me, and I'm more than willing to help you. All right. Okay, so that's it, folks. Or I should say, ladies. I'll see you guys on Tuesday. All right. Take care and enjoy your weekend.